Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good, Better, Best Online Videos for more video content. Rate and extent of reaction, okay, grade 12s, which will be part of your June exam, which will be part of your final exam, okay. In grade 11, of course, we had learned about energy and chemical change, okay. We looked at also the energy change that happens in reactions. We had looked at potential energy diagrams, all right. Obviously, we looked at endothermic reaction, where the heat of our products was greater than the heat of our reactants. Okay, so we had enthalpy that was greater than 0, and if it was exothermic, we had enthalpy was less than 0. If you remember those potential energy diagrams with the activation energy and the activated complex, etc., etc. All right, so slowly but surely we're going to evolve that, or we're going to evolve from that rather. Just make some space here on my working space. All right. During a chemical reaction, the rate at which and the extent to which reactants change into products, they do play a crucial role in what actually forms. During the industrial production of substances, it is important to obtain a high yield at a high reaction rate, as economically as possible. All right. So high output, all right, at quite a fast rate. Right? In other words, per unit time or per second, right? Because time is money and time is of the essence and all those sayings that we know about time, etc., etc. Okay? As economically or as cheaply or as affordable as possible. Okay. What is meant by the phrase chemical reaction, or what is meant by the phrase rate of reaction? Let's consider the chemical reaction of reaction or reactants are becoming products. All right, capital P. Some reactions take place instantaneously. All right, so we have some instantaneous reaction. Instantaneous word I sometimes struggle to spell. Reactions. Okay, and an example of that would be the combustion of petrol. Of petroleum. Drop a lit match or something lit rag into a petrol tank, and you will not be able to run fast enough before the ground explodes from underneath you. All right, it will happen so fast. All right, no one will notice. You won't even know that you did, even when you did. Okay. However, other reactions such as iron takes longer. So iron, we know that the reaction that happens with iron is rusting or rust. All right, this reaction takes much longer. Okay, this happens over time. All right, rust doesn't happen immediately or instantaneously. Rust happens over quite a long period of time. Now, the reaction rate does describe, all right, that's basically what it is. The reaction rate describes how quickly, take that S away there. All right, it describes how quickly or slowly, in the case of rust, products form. Okay, how quickly or how slowly products form, and also the reactants are used up during the reaction. Okay, now the reaction rate does indicate the change in the concentration of the reactants or their products per unit time. All right, so remember, it's the change in concentration, but we can also define the reaction rate by also looking at the change in the number of moles, or the change in the amount of liquid, or the change in the mass at the same time. That will tell you how they want that to be defined. Okay. So the formula for calculating the average reaction rate, so if we have a look at average reaction rate, okay, is equal to the change, I'm going to write it out in words first, the change in the amount of reactant or reactants, all divided by the time of reaction, which I'm going to put in brackets, which is basically equal to change in the amount, so the number of reactants in R, which is the mole, by the way, change in time. Okay, the mole is the amount of substance, so the change in the amount of reactant divided by the time. So the amount of a substance is the mole. All right, that's why you see N. All right, but also can be the change in the concentration. All right, so we can also calculate it by taking the change in. If you have the concentration change and per unit time, you'd also have delta C there as well. This can also mean not just the amount of moles of reactants, but can also be the change in the amount of products for P divided by time. Alright? Average rate of reaction can also be calculated by taking the change in the amount of products over the change in time. Now we can monitor the rate of the reaction. Okay? This is a couple of points that we need to look out here. We can monitor rate of reaction, ROR, alright, by one, looking at the decrease in mass. Right? Looking at the decrease in mass of reactants. Alright, per time. So we can also look at the rate of the reaction by taking a look at the decrease in the mass of the reactants. Alright, we can also have a look at the increase in mass or volume of a product. Alright, in this case that'll be a gas that's released, and that's also per unit time. Okay, another way we could also do is have a look at obviously the change in concentration. Let's look at the change in concentration of the reactants or products per unit time. Okay, of reactants, cap in brackets R or brackets P per unit time. Alright, and we can also have a look at the time it takes for the color to change of a certain reaction, etc., etc. Okay, those are all the ways that we can actually monitor a rate or extent of reaction. Alright, rate and extent of a reaction. Okay, not just by looking at only the amount of something or only the change in the amount of moles, but looking at the change in concentration, the mass or the volume, and we could still calculate or still come up with a suitable answer for determining the rate or the extent of a reaction. Right, so there are factors that do affect the rate of a chemical reaction. There are actually 5 factors. Okay, number 1, the nature of reactants. Okay, we're going to list them all first. Okay. Number 2, the temperature. Okay, when I say temperature, I mean the temperature at which the reaction takes place. 3, the concentration of a liquid reactant. Alright, the concentration of a liquid reactant or pressure of a gas. Alright, so it could be the concentration of a liquid reactant, alright, or the pressure of a gaseous reactant. Gaseous, right, reactant. Okay, a compressed gas does have a higher concentration, so hence why it's both written in one line. Surface area of a solid. And number 5, the use of a catalyst. Okay, the effect of each factor can be explained in terms of the collision theory, okay, which we're not going to aim to attempt to explain right now, okay, but collision theory does play a factor in each of these factors that affect the rate of reaction. But probably one of the most easiest one to possibly just have a look at would possibly be the reaction surface area of a solid, or the surface area of a solid. All right. Remember, take a block of cheese versus grated cheese. Now, a block of cheese would be considered my example of just a solid right now. It's got nothing to do with science at the moment, okay? Sorry for everybody that's lactose, like myself. I think I'm lactose because there's my reaction to dairy products has not exactly been very good over the past couple of weeks, or in fact for this year. Might just be a phase I'm going through, but I should probably go to the doctor and take a lactose test. But anyway, I digress. Back to cheese, the example of cheese. So let's take a block of cheese, mate, all right? And obviously it's not a fairly block, it's not a, I mean, if you see a blue block of cheese, you know, the cheese that we see there, you know, when you go buy cheese, whatever, it might not look very big. As soon as you grate that thing in a grater, it looks like you have what? It looks like you have more cheese than what you had to begin with, when it was in its block form. All right? It's grated into smaller pieces. All right? So now it looks like you have more cheese. You could possibly eat more salty cracks with your cheese now than what you could if it was in block form, because you probably would have cut it a bit too thick, or blah 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 blah. Right? Same thing with the reaction surface of a solid area, which I'm just explaining number 4 quickly, is that when a solid reactant is more finely divided, in other words, if you have a solid in crystal form versus a solid in powder form, powder obviously has a greater surface area, is more substance to react with. In other words, there are greater collisions or greater surface area for collisions to occur, all right, in the reactions. You'll have more effective collisions per unit time, and the reaction rate will therefore increase, all right? That is also a reason why, if we have, if we bring it back to chemistry, let's take a tablet, all right, or an antacid tablet, especially, not a Panado, an antacid like Barocca, or Slowmang, or Effaflu. All right, those are antacid tablets. Okay. That's why or even a headache tablet like Grandpa, which is in powder form, you know, and not in tablet form. You'll find out that reason why people like to take Grandpas for if they have headaches is because it provides relief much quicker than a tablet in solid form, because now your stomach must still break down the tablet that was in solid form, whereas the powder, greater surface area for collisions, more effective collisions to happen. Guess what happens? It goes straight into the bloodstream. It goes straight into the stomach, straight into the blood, because it reacts way quicker because the surface area is larger. So that was a better reaction, a better example than maybe the block of cheese. Okay, so just explain one there. I will go into details, more effective details there once I've explained collision theory a little bit more in depth. Okay, so these 5 factors we must know, because they are examinable. They can be a multiple choice question, a 1-word question, or possibly a 1-mark question in the exam, where they ask you to name 2 things or name 1 thing that could affect the nature of this reaction. We must know to either speed it up, or to either decrease it, or just affect it in general. We must know these 5. Okay. Alright, so with collision theory, okay, according to it, particles, atoms, molecules, or ions can only react when they collide with each other. That makes perfect sense, because when we were learning chemistry for the first time, we probably were all showed videos about how water has water particles, and how the particles vibrate with each other, and that causes some type of reaction. In other words, they vibrate so fast that the water starts to boil. So because the particles are vibrating so fast, the water is boiling. Obviously, the temperature was increased. We also saw previously factors that will affect the reaction rate is actually temperature. Increasing temperature, increasing the kinetic energy of the particles results in more collisions, effective collisions per unit time, thus increasing the reaction rate. You didn't have to be smart to know that if you just understood how temperature worked. Okay, but coming back to collision theory, if you want to have a look at effective collisions, okay, not all collisions do result in a reaction though, right? Otherwise, all reactions will be fast. Okay, rust, there's no collision theory applied there. It just happens, otherwise it would have happened very fast. It actually doesn't, it happens very slow. The rate of the reaction will be determined by, number one, the number of reactions. So that's NO there with the dot there, number of reactions, or not reactions, sorry, take that word out. Number of collisions per unit time. Okay, so number of collisions per unit time, which is also known as the frequency of collisions. Frequency of collisions, right? Number one. Okay. Then there's also the energy of colliding particles. Okay. And there's also the orientation of the particles that collide. Okay, collisions that result in a reaction are called effective collisions. Okay, effective collisions are collisions that result in reactions. Cool. Okay. So when it comes to the frequency of collisions, that's the number of collisions per second or per unit time, which actually is per second. Okay. What is that dependent on? Okay. The frequency of collisions. This is going to wrap up a bit of collision theory. Just a bit of it. We're going to have a look at frequency, energy, and also orientation. Okay, but with the frequency, the number of reactant particles per volume. All right. So let me just explain this. So number of reactant particles per volume. Or per unit volume. This can only be increased by increasing the concentration of a solution, or by increasing the pressure of a gas. Because if you increase the pressure, it'll have a higher concentration. At a high pressure, the gas particles will be compressed into a smaller volume. Right? If your volume is smaller, your concentration will be higher. So the particles will collide more frequently. Thus will obviously result in more effective collisions per unit time. And then, of course, the average kinetic energy. Of the particles. The average kinetic energy of the particles. This can be increased by increasing the temperature, right? Increasing temperature increases the average kinetic energy of particles of the reaction mixture. The particles will move more frequently and more rapidly, and they will collide therefore more frequently, resulting in more effective collisions. All right, because we increase the temperature. Okay. That also leads into the energy of particles. If you increase the temperature, you increase the kinetic energy in the reaction. All right? That means your kinetic energy increases, means that your particles collide more frequently and more effectively, resulting in a faster or quicker reaction. Okay, and we obviously know what that is called. Collisions between particles are effective and result in a reaction if the particles have a certain amount of kinetic energy, which is called the activation energy from grade 11. All right. And that grade 12s is the first introduction session of rate and extent of reaction. Please stay tuned for more, where we will continue with this broad topic.